Let's dive right in and crack open the core engine behind every modern offshore rig, the variable speed drive. You know, if you've ever stood on a drill floor, you know that connecting a driller's joystick to a drill bit thousands of feet below relies entirely on controlling massive amounts of electrical power. Today, we're focusing on exactly how that power is harnessed. Now, a VSD might seem like this intimidating black box humming away in a switchgear room, but we're going to change that completely. Because if you open any VSD cabinet on any rig in the world, you are going to find the exact same 3 stages doing the exact same 3 jobs: rectify, store, and invert. Once you grasp those 3, pretty much every drive schematic out there suddenly makes perfect sense. Here's our roadmap for today. 1. Inside the VSD black box. 2. Why AC motors win. 3. Protecting the rig grid. And 4. Drawworks and zero-speed torque. Section 1. Inside the VSD black box. Deconstructing the drive. Okay, trace the journey of electricity here, moving from left to right. The raw supply comes in on the left, passes through the rectifier block, moves right into the DC link in the middle, and is finally pushed out through the inverter on the right to actually drive the motor. It takes this complex wall of electronics and turns it into a highly logical linear flow. Let's break that down. Step 1 is the rectifier. So fixed frequency AC comes in from the grid, say 50 or 60 hertz, and a diode bridge converts it to pulsating DC. The rectifier doesn't care at all about motor speed, it just makes DC. Step 2 is the DC link. This uses a bank of capacitors to smooth that pulsating DC into a really stable, flat reservoir of power. And then step 3, the inverter, well, that's where the magic actually happens. It uses highly responsive IGBT switches to literally chop that stable DC back into an AC waveform, but this time at whatever variable frequency and voltage the motor actually needs. So let's do a quick check here to see if you caught the secret to why a VSD is so incredibly useful. Think about it. How can a VSD output a highly specific 5 Hz to a motor when the main rig grid is stubbornly feeding it 50 or 60 Hz? Which specific stage makes that frequency translation possible? It's the DC link. It basically acts as an energetic buffer, giving the inverter total freedom to synthesize whatever frequency the motor needs, completely independently of the grid. By totally decoupling the input from the output, that stable reservoir of DC power gives us the literal definition of variable speed control. Section 2. Why AC motors win. The maintenance battle. Just look at this contrast. It perfectly illustrates the harsh reality of the past versus the present on a rig floor. On the left, you've got the demanding, hands-on nightmare of maintaining a DC motor, dealing directly with an exposed, sparking commutator. And on the right, the modern AC alternative, a fully sealed, robust block of engineering. You can immediately sense which one survives better in a saltwater, high-vibration environment, right? Older DC drives controlled speed by varying armature voltage directly. And sure, while that's simple in theory, it requires brushes and commutators. You know, physical contact points that wear out, they spark, and they just demand constant scheduled maintenance. A modern AC VSD, on the other hand, controls speed electronically. That means the AC motor has 0 mechanical wear parts in the power path itself. It's a closed structure where your primary maintenance is really just checking the bearings. Now, thinking about a rig where downtime literally costs thousands of dollars every single hour, what do you think the biggest financial and operational win is here? Like, what specific headache did engineers eliminate by moving away from DC motors? Absolutely. It's eliminating the brush and commutator system entirely. By doing that, we instantly wipe out the most frequent, labor-intensive, and frankly miserable maintenance task on the entire rig. No more scheduling downtime for brush replacement, no more tearing down the motor for commutator resurfacing. It's just a massive leap in high availability, purely because we deleted the most vulnerable wear items. Moving to Section 3, protecting the rig grid, the electrical win. Let's look at the grid side now. Old DC thyristor systems used to tank the power factor at low speeds, drawing tons of wasteful reactive power. But modern AC drives hold a constant high power factor. Notice that flat line across the entire speed range. Because of the diode rectifier front end, AC VSDs operate incredibly efficiently. And this completely eliminates the need to install and maintain those bulky, expensive capacitor banks just to correct the rig's power factor. Then there's the startup. Starting a massive drilling motor direct online pulls a violent inrush current spike. We're talking sometimes 6 to 8 times its normal running current. That slams the grid, stresses breakers, and visibly dips the ship's bus voltage. But follow the VSD-controlled curve here. The drive smoothly ramps the motor up through controlled acceleration, mitigating that spike entirely so only active power is drawn. It's so much smoother. And on top of all that, AC drives inherently reduce network harmonics. Harmonics are essentially electrical noise that distorts the power supply, right? And they're proportional to the line current. Because the AC VSD manages current so incredibly efficiently, those harmonics are kept low. Plus, engineers can push those harmonic distortions down even further by using multi-pulse rectifier designs, like 12-pulse or 24-pulse transformers, which effectively cancel out specific harmonic frequencies altogether. Finally, Section 4, Drawworks, Zero Speed Torque, the Operational Climax. Now this is the ultimate test, and it proves the true power of AC technology. Look at this torque curve for the drilling motor. It delivers full, 100% rated torque starting right at exactly 0 RPM. It doesn't need to spin up to grab the load at all. Even better, it can hold that maximum torque at 0 speed for extended periods, theoretically years, without overheating. And that is all thanks to precise current management by the drive. The stakes here are absolutely massive. Older motors required a minimum RPM to actually develop full torque, which risked a deadly phenomenon known as uncontrolled slip. I mean, imagine holding a massive drill string steady to make a connection, and the motor slightly drifts because it just can't hold torque at 0 speed. The AC VSD completely erases that danger, making the rig fundamentally safer exactly when you need to be dead still. So that brings us to a final, pretty game-changing thought to leave you with. We've seen how incredible OneDrive is at rectifying power, protecting the grid, and delivering that 0-speed torque. But a rig has dozens of massive motors. What happens to our entire electrical architecture if instead of isolated drives, we link several of them together to share one massive DC link? Imagine the energy savings if a braking drawworks instantly fed power over to a hoisting top drive. It's a fascinating design shift, and it completely changes the future of offshore efficiency.